Our next slammer today is David Goldberger. He is a master's student from the Department of Physics, and his topic today is breaking more stuff with X-rays.
Thank you very much for that introduction. So I'm lucky enough to do research with Dr. Michael Pravica joining us today. And I've been here at UNLV since this past January of 2017. Now, just before I started, Dr. Pravica had this really fascinating result. He found if you take an inert white powder called strontium oxalate, and you irradiate it with X-rays. Basically, you blast it with X-ray photons. You can actually cause it to break apart, and then it'll reform into this brand new material that we think has never existed before. Now, as a physicist, it's not quite enough just to say that I can break stuff apart. I have to know how it's breaking apart, or at least I have to know how to break more stuff with X-rays. So we went to do an experiment at the Advanced Photon Source at the Argonne National Lab in Chicago. And it's a really amazing facility. It's one of the only places in the world where they can produce X-rays at high enough energies and high enough intensities to actually break apart materials. They can do that because they've got an X-ray beam there that's about twice as bright as the sun. Now, when we're there, we know that there's two aspects of our experiment that we can control very well. The first is the amount of pressure that we apply to our samples of strontium oxalate. And we control that by squeezing our samples in between the tips of two diamonds in what we call a diamond anvil cell. The second aspect that we can control very well is the energy of the irradiating photons. And that's controlled by a complex system of X-ray optics at the Advanced Photon Source. So we essentially have these two knobs that we're going to turn. We turn up the energy and see if that leads to more or less stuff breaking apart. And then we turn up the pressure and see if that leads to more or less stuff breaking apart. Now, what I'm showing in these two figures that I've actually reproduced from a paper that we published in the Journal of Physical Chemistry A, on the y-axis in each one you can see the decomposition yield as a percentage. You can think of that as the amount of material that we're breaking apart. And on the x-axis over there we have the pressure, and over here the energy. In the energy study we see a cutoff energy right around 16 kilo-electron volts. So if you're below 16 you don't break down much material. But if you're above 16, you break down a lot of material, and you break the most when you're at 20. On the pressure side, we see a very complex dependence, but we do see a dramatic increase in the amount of material that you break down if you pressurize your samples to 1 GPa. That's 1 gigapascal, and that's about 10,000 times the pressure that you feel right now from the atmosphere all around you. So still a pretty significant amount of pressure. Based on these results, we're actually hypothesizing that we found a brand new way to do chemistry. Since we're doing chemistry in a new way, we're hoping we can use these techniques to make brand new materials. Materials that might have exciting new electronic and optical properties. As a last note, I'll also mention we're hoping that this system is going to give us some insight, potentially into the origins of life in the interstellar environment. So thank you very much for your attention. Thank you to the Grad College and to our judges one more time. Thank you.